Have you ever seen or laid reinforcing mesh continuously through control joints? What happens when steel mesh is in a concrete path and the joint is forced up and hinged? Once the slab starts to hinge, minor cracks appear in the concrete. These cracks penetrate the slab and expose the mesh to the elements. Rain can now seep through the cracks, causing corrosion of the metal, the first step in concrete cancer. Once enough force is applied to the slab, all the mesh strands snap, one by one. Without the mesh to support it, the broken concrete won't reliably transfer load and will quickly displace, resulting in a tripping hazard. After studying mesh failure when used through control joints and seeing the destructive effects firsthand, we chose to run a direct comparison between mesh and TripStop. Our tests have been verified by independent engineers who have written detailed reports that outline their findings. Our testing regime was developed by RMIT University in Melbourne, Australia, and used as a base model for all our independent tests. The testing process is shown in detail on our website and is backed with movies. We've published all the engineers' reports so that everyone can see the irrefutable evidence that mesh should not be used through control joints. The reports outline full details of each test performed and offer an in-depth independent analysis of the testing process, materials used and forces applied throughout testing. This path was 100mm thick and the control joints were spaced at 1.5 metres apart. We used centrally located SF72 mesh on bar chairs and 25 MPa 80 slump concrete. The concrete was slump tested and backed with a written report from the concrete supplier Vimix. All testing was witnessed by an independent engineer who has provided a detailed written report on the testing process. This video has been sped up for display purposes. When testing the mesh reinforced path, we found that the path began cracking as soon as any lift was applied. Even when the slab lift was under 10mm, cracks formed around the control joint and spread quickly from the top to the base of the slab. These cracks allow water into the slab, which will attack the mesh, which is now exposed. At 20mm lift, cracks also started forming away from the control joint, effectively curving the slab and creating water entry points in multiple locations. These additional cracks severely weaken the slab, leaving the mesh to bear the load. At 55mm lift, the mesh began to fail. As can be seen here, the load shift is violent and dramatic. At just 67mm of lift, all the mesh strands had failed, resulting in an immediate reduction in load and an aggregate interlock. From this point on, there was nothing but broken concrete to keep the slabs joined together. We continued testing, lowering the slab and lifting it a further 2 times, measuring the displacement each lift. Once the mesh had failed, the displacement was clearly visible. The displacement on the third lift was measured at 11.2mm. To provide a direct comparison, we then tested TripStop under identical conditions. We used the same test bed and testing procedures to measure the lift, displacement and the force applied. TripStop is designed to transfer the load evenly between the slabs and allow uplift, meaning that the slabs can smoothly lift and fall with minimal displacement. As TripStop is made from extruded UV stabilised PVC, it doesn't suffer from corrosion. TripStop can easily handle 108mm lift, which is a 1 in 14 rise and a 1.5 space slab with minimal displacement. Mesh can't do this. The steel test bed is 5 metres long by 1.5 metres wide by 900mm high. This path is 125mm thick and the joints are spaced at 1.5 metres apart. All of our tests use centrally located SF72 mesh on bar chairs and 25 MPa 80 slump concrete. This test was slump tested and backed with a written report from the concrete supplier Holcim. We found that the mesh reinforced path began cracking from the top to the base of the slab, with the mesh stretching as soon as there was any uplift. The joint spalled at the base and the mesh continued to be stretched and thinned as it was subjected to more and more uplift. The first strand of mesh snapped at just 40mm lift. Water could then get in, run down the crack and attack the weakened exposed mesh. Whoop. Up to 61.
It's getting easier actually.
All the strands had completely failed at just 62mm of lift. The open joint now relied on aggregate interlock, which won't reliably transfer load. How long will various grades of weakened and stretched mesh last in exposed situations?
But that would hold a lot of water in there, wouldn't it? I imagine it wouldn't take much to rust it out.
This is what happened when some weight was applied to the slab. A major spall and about another 10mm drop onto the next level of aggregate. This will fail later. Aggregate interlock can't reliably transfer load. Mesh can't reliably transfer load either. TripStop can and will reliably transfer load.